Hey, hi, good morning. Welcome to the class. So, today's class is about pulse shaping. So, today's class is about pulse shaping and intersymbol interference. One second, let me check if it has started streaming. Give me a second. Okay, fine. So, let us start the class. So, this class is about intersymbol interference and pulse shaping. Okay, so very crucial concept and very important. A little tricky concept as well. So let us understand this. So if you want to transmit the bits, let's say if you want to transmit 1 or 0, digital communication, we transmit bits. And we cannot transmit bits as it is. So we have to convert the bits into voltages and then only we can transmit, right? So we have to convert these bits into voltages. And basically, what is the basic way of converting bits into voltages? We convert 1 into a positive rectangle like this. And we convert 0 into a negative rectangle like this. If you are using a non-written zero scheme, this is what you do. And the width of the rectangle will be TB. So this is how you transmit bits in the form of voltages if you want to transmit bits through a channel. So bits, if you want to transmit through a channel, you have to convert the bits into voltages like this, two different voltages. So if you are transmitting this rectangle, if you want to transmit a bit, you have to transmit these rectangles. Then if you are transmitting these rectangles through a channel, what happens? Let us understand that. So if you're transmitting rectangle, so let me say rectangle pulse is P of t. And what is the Fourier transform of P of t? That is really important. So Fourier transform of rectangle is sinc function. And whatever is the width of the rectangle will decide the null point of the sinc function. Whatever is the width of the rectangle, inverse of it will be the null point here. And this null point value is, the width is TB, reverse of it is 1 by TB, and 1 by TB is same as RB. RB means bit rate, TB means bit time, right? So the Fourier transform of a rectangular pulse is a sinc function. So this sinc function, if you observe, it is having infinite frequencies. Okay, so the frequencies range from minus infinity to plus infinity. So they range from minus infinity to plus infinity. So the bandwidth of this signal is infinite, right? So if the bandwidth is infinite, so if you pass this signal through a channel, through a band limited channel, so what happens is, band limited channel means what? The limited bandwidth channel. All channels, which are all the practical channels, are all band limited channels only, right? So if you pass this signal through a band limited channel, what happens is, the band limited channel limits the bandwidth of the signal. So if you pass this signal through this channel, so I'm talking in frequency domain here. If you pass this signal through the channel, what happens is, a part of this signal will be allowed by this channel, but the remaining part will be blocked by the channel. Correct? Will be blocked by the channel. Right. So only the first loop. Here I have taken BC is bandwidth of the channel. Here I have assumed that the bandwidth of the channel is 2 RB. That's why I have plotted like this. The bandwidth of the channel need not be exactly 2 RB. It can be more than that or less than that also. We don't know. So for what channels the bandwidth will be like this? For example, wired channels. For wired channels basically they behave like low pass filters. They allow frequencies till a certain frequency. For example, if you take twisted pair cable bandwidth is only 500 kilohertz, whereas coaxial cable bandwidth is 500 megahertz. But there is some cutoff frequency, high cutoff frequency, which means they behave like more or less like low pass filters. They are not low pass filters, but their behavior is like low pass filters, right? So for example, I have taken one channel whose bandwidth is like this. Now definitely, whatever is the bandwidth of the channel, it doesn't matter. When you pass the signal, some side lobes will be cut off. Correct? So this signal, when you pass through this channel, band limited channel, so few side lobes may be cut off or more side lobes may be cut off, but some of the side lobes will be definitely cut off. So when the side lobes are cut off, this is the output of the channel, which means at the receiver you are going to receive this signal. So if you are receiving this signal, so what is the inverse Fourier transform of this signal? This is what we have transmitted in time domain, which means this is what we have transmitted in frequency domain. But at the receiver we are receiving this, not exactly this. The inverse Fourier transform of this one is rectangle, but the inverse Fourier transform of this one is definitely not a rectangle. Correct? So the inverse Fourier transform of this is not rectangle because the shape has changed in frequency domain, which means the shape in time domain also will change. Here you are cutting off some high frequencies, which means the fast change here. In the rectangle, there is sudden change here, fast change. Fast change corresponds to high frequency. Here, the high frequencies are cut off by the band limited channel. Because of that, what happens is, in this signal, whatever the fast changes, they will be removed. And the signal becomes little smoother because these high frequencies were cut off. Fine. So one simple funda is, here some frequencies are missing or the shape and the Fourier transform is different, which means in time domain also shape should be different. Whether it is this shape or not, it doesn't matter. What is important thing is the shape will definitely change in time domain as well, because in frequency domain the shape is changing because of band limited channel. Right. Having understood this, what is the problem with this? What is the problem with this? At the receiver, what we do is, so at the receiver, what we do is, we do sampling actually. At the receiver, we do sampling. So for example, every TB time you are going to sample. So at 0 time you are sampling. At TB time you are sampling. At 2 TB time also you are sampling. You are sampling, and if the value is positive, since you are transmitting a positive value, positive voltage for 1 bit and negative voltage for 0 bit, the midpoint of positive voltage and negative voltage is 0 basically. So if you receive any voltage which is more than 0, you'll understand that okay, 0 is transmitted. And if you receive any voltage which is less than 0, you'll understand it as 0 is transmitted. Okay, right. So based on the voltage, whether it is positive or negative, you are deciding whether it is 1 bit or 0 bit. So for every bit, you have to have one sample. Okay, you cannot take all the values. You have to take one particular sample value and you have to analyze it. So what we do is we sample it every TB seconds. At TB we sample, at 2 TB we sample, at TB we sample and we decide the first bit. At 2 TB we sample and we decide the second bit, and so on. At every TB seconds, starting from 0, at every TB seconds you sample and you decide based on the voltage. You decide whether it is positive voltage or decide negative voltage. If it is positive voltage, you understand it as 1 bit, and if it is negative voltage, you understand it as 0 bit. Now here if you observe, this is the actual signal that is transmitted. Same discussion I am doing actually. Same discussion I am doing. Instead of one rectangle, I am talking about, so if you observe, previously I have talked about single rectangle. But what we transmit practically is not one rectangle, we send multiple rectangles. Okay, mix of multiple positive and negative rectangles, because we want to send not just one bit, we want to send multiple bits. So if you want to send multiple bits, the transmitted signal is going to look something like this. So the Fourier transform, this total signal is going to look something like this only. For one rectangle also Fourier transform is sync, the other rectangle also Fourier transform is similar sync. So this rectangle Fourier transform is also same sync only. Now this signal or this signal, they both represent the same signal, but this is in time domain, this is in frequency domain. Now instead of one rectangle, we are passing this total signal or this total signal through a band limited channel. So if you pass through band limited channel, what happens? Band limited channel will remove some high frequencies. If it removes some high frequencies, this is what we are receiving at the receiver. Now, so since the shape changed in time domain, frequency domain, the shape should change in time domain as well. Okay. So earlier I have plotted one rectangle and one pulse here. Here, since I'm taking 3 rectangles, I'm plotting 3 pulses here. Okay, 3 different, not rectangular pulses, but some other pulses. Because some high frequencies are cut off, these fast changes will not be present. Now this rectangle will be received like this, and this rectangle will be received like this, and this rectangle will be received like this. Now what we do at the receiver, we are going to sample. Okay, we are going to sample. So we are going to sample at 0, we are going to sample at TB, and we are going to sample at 2 TB. Here the total signal, here I did not add these signals. Whatever we receive at the receiver is addition of these three signals. Okay, if it is addition of these three signals, it will look more complicated than this. Okay, right. So let us understand this. Here, why are we taking it as cut off? Here either you should receive, let me say this is some 5 volts, and let me say this is some minus 5 volts. And so if it is 5 and minus 5 that you are transmitting for 1 and 0 bit, then why are we taking the cutoff as 0? Because you may not receive 5 volts because of noise. Because of noise, you may receive it as 6 volts or 4 volts or 3 volts or 2 volts, 1 volt, minus 1 also sometimes. Okay. Similarly, when minus 5 is received, because of noise, minus 5, we may not be receiving exactly minus 5, we may receive minus 4, minus 3, minus 2, minus 1, 0, 1, 2 also. So that's why we are putting some threshold. So there is more chance that if you transmit 5 volts at the receiver, you may receive with noise, you may receive a voltage which is more than 0. There is high probability that you may receive voltage which is more than 0 because you are transmitting. You are supposed to receive 5. Because of noise, you are receiving something around 5. Okay. Similarly, you are supposed to receive minus 5. You will be receiving something around minus 5 because of noise. But in a very rare case, when you transmit 5, you may receive a negative voltage. That's a very rare chance. And in that rare chance, you will understand the bit wrongly. Okay. So here you are supposed to receive 5. Because of noise, you may receive any voltage which is other than 5 also. But most probably you will receive any voltage which is more than 0 only. But very rare case, in a very rare case, you may receive a voltage which is less than 0. And when is that possible? When the noise is very huge, then that may be possible. Fine. So along with noise, you may not be receiving 5, you may be receiving something like 4 or 3 or something like that. Similarly, instead of minus 5, because of noise, you may be receiving minus 4 or minus 3 or minus 2, something like that. Okay. Very rarely, this minus 5 may be received as plus 1 or so on. Because noise, having that much amount of noise is very rare probability. Okay. Fine. Here, don't think that sample value we are going to get exactly 5. The point I want to convey here is you may not get exactly 5. You may be getting something different from 5 because of noise. So that's why we are having some threshold. And what is the threshold value that you are using? 0. If you are receiving any voltage which is greater than 0, okay, you are understanding it as 1 bit. And if you are receiving any voltage less than 0, you are understanding it as 0 bit. Same concept let us apply here also. So this signal we are passing through channel. Since it is a band limited channel, it is cutting off some frequencies in the signal. So because it is cutting off high frequencies, what is happening is the fast changes which are present in the signal, the fast changes, sudden changes, they will not be present in the received signal because high frequencies are cut off. High frequencies, these fast changes correspond to high frequencies. Right. So this is how the signal looks like. Now, if you observe, since the high frequencies are cut off, the rectangle has spread out. The rectangle has become smooth and it has become wider. If the rectangle has become wider, what happens is one pulse will interfere with the next pulse. And this interference is what we call as intersymbol interference. So interference of one pulse with the next pulse is what we call as intersymbol interference. And what is the problem with that? Let us see. So this pulse is received like this. So we are supposed to receive this sample value. Let us assume this is 5 volts. But because of this value, the second pulse is interfering with the first pulse. Let me say this voltage is something like some minus 1, for example. And because of this voltage is almost zero value. So let me say this is 0.2, something, for example. So this second symbol is interfering with the first symbol, or second pulse is interfering with the first pulse, and third pulse was also interfering with the first pulse. Similarly, first pulse is interfering with the second pulse, and third pulse is also interfering with the second pulse. So because of this, what happens is there is more chance of errors. Here, very rarely we may get errors, but here we may get errors little bit more often compared to this. So why? Let us understand. Basically, you are supposed to receive 5. You will receive 5 if you are transmitting through infinite bandwidth channel. If you transmit through infinite bandwidth channel, you are not going to get this. You are going to get exactly this. But we don't have infinite bandwidth channels. We are having band limited channels only. So if you transmit through band limited channels, this is how the signal looks like when you receive it at the receiver. So you are supposed to receive plus 5. Now because of this interference from the second symbol, what is happening is some minus 1 is coming out. So what is the sample value that you are going to get here? It is going to be plus 4. Instead of 5, we are going to get 4. And along this point 2, it will become 4.2. So you are supposed to receive 5, but you are receiving only 4.2 without noise. But with noise, what happens? You may receive voltage which is less than this or more than this, which you are going to receive a voltage which is different from 4.2. So what is happening is ISI intersymbol interference is reducing the voltage. Without noise only, it is reducing the voltage than expected voltage, which means because of noise, what happens is this 4.2 may become -1, -2, and so on. Okay, more often than this one. So you are getting a voltage which is less than the expected voltage, which means that will increase the chance of getting a error. Right? If you understand the second symbol, then you'll understand more clearly. See this one, the second symbol is having interference from the first symbol as well as the third symbol. Now here I am expecting to receive -5, and let me say because of this one you are having some 1 volt, and because of this one also another 1 volt. So totally, so if you add all these things, what happens is you are supposed, at this point you are supposed to receive -5, but because of this first symbol and third symbol, 1 plus 1 is 2 volts, -5 plus 2 volts is -3. So basically you are supposed to receive -5, but you are receiving only plus -3, which means your expected voltage is -5, but you are receiving only -3 without noise. But now when you add noise, what happens is there is more chance of errors, because when it is -5, you are having certain probability of error. But when you are guaranteedly receiving -3 because of ISI, what happens is there will be definitely more chance of errors. In the previous case, there is a chance of noise can be up to 5 volts. If the noise is more than 5 volts, then only we are having a problem. Correct? If the noise is more than 5 volts, then the voltage received at the receiver will be negative value. If it is negative value, you will understand it as 0 bit. You have transmitted 1 bit, but you are understanding as 0 bit if the noise is more than 5 volts. Okay, but here, if the noise is more than 3 volts only, you are going to get an error. So which means the probability of error has increased. The chance of getting an error has increased because of this ISI. So this is what we call as ISI. Here you can clearly see what is happening. So we are having intersymbol interference. So you can understand the meaning of it from the words itself. Intersymbol interference. One symbol is interfering with the neighboring symbol. So that is what we call as intersymbol interference. Fine. So why are we getting this? We are getting this because of band limited channels. Whenever you transmit rectangular pulses through band limited channels, we are definitely going to get intersymbol interference. So we want to minimize it. So how to minimize it? How to minimize it? Let us see. Intersymbol interference is introduced when a rectangular pulse is transmitted through a band limited channel. Perfect. So that is what we have learned till now. Intersymbol interference is introduced when a rectangular pulse. Rectangular pulse is like what is happening? It is infinite bandwidth signal, right? Practically we say some finite bandwidth, but basically it is having side lobes which extend till infinity, which means a rectangular pulse is like a, ideally speaking, it's an infinite bandwidth signal. It's not a band limited signal. Rectangular pulse is not a band limited signal. Definitely not a band limited signal. Okay, practically we say the bandwidth of this pulse, rectangular pulse, as first null point. Okay, first null point is RB. So generally, practically speaking, we say the bandwidth as RB, but ideally speaking, it is having infinite bandwidth. Right. So how to avoid ISI? It's very simple. To avoid ISI due to band limited channels, what we can do, we cannot control the channel. What we can do is we can control the signal. So transmit band limited signals through band limited channels. Instead of rectangular pulse, use some other pulse. Okay, use some other pulse. Instead of, if you are using rectangular pulse has fast changes in it. If it is having fast changes, it will have high frequencies in it. So that's why it is becoming band limited. Sorry, it is having infinite bandwidth. So to make the signal band limited, it should not have sudden changes like this. It should not have sudden changes like this. If the pulse is like a smoother pulse, instead of having sudden changes, if it is like a smoother pulse, then definitely it will be a band limited pulse. So the idea is, anyway, we cannot have infinite bandwidth channels. So what we can have is we can have finite bandwidth signals. So we can have band limited signals transmitted through band limited channels. If band limited signals are transmitted through band limited channels, then there is no problem of ISI, correct? So if the signal that you are transmitting is not having these many side lobes, if the bandwidth of the signal that you are transmitting is limited, then when you pass through the channel, you will be getting the exact same thing, which means there will not be any change in shape in time domain as well. If the change in shape is not happening in frequency domain, in time domain also change in shape will not happen. So if the signal is not having these many side loops, if it is limited in bandwidth, then if you pass through channel, you are going to get the exact same shape at the receiver also, which means in time domain also you are going to get the exact same shape, right? So to make the signal to be transmitted band limited, pulse shaping should be done. Pulse shaping should be done. Give me a break for 1 minute. Hello. Sorry for the interruption. Let me continue. Right. To make the signal to be transmitted band limited, if you want to make the signal band limited signal, what we can do is we can do pulse shaping on rectangular pulse. So what I mean by this is you can convert. Basically, you're having ones and zeros, ones and zeros. Now what you can do is you can use an NRZ scheme or an on-off scheme to convert these ones and zeros into rectangular pulses. So 1 is converted into positive rectangle, 0 is converted into negative rectangle, and 1 is again converted into positive rectangle, and 0 is converted into a negative rectangle. Okay, right. So this is how the signal looks like. This is how the actual signal looks like if you are passing through NRZ. So this signal we can pass through the channel directly, but the channels are band limited. But the signal is having, ideally speaking, infinite bandwidth, more side lobes. But when you transmit this signal through band limited channel, what happens is it will cut off some frequencies, which means the shape of these pulses will change. So that's why, so when the shape of the pulses changes, one symbol will interfere with the neighboring symbol. So that is what we call as inter-symbol interference. To avoid that, what we can do is we can include this block. What block is that? We can include this block, which we call it as pulse shaping. Pulse shaping. So what it will do is it will change the shape of the pulse so that it will have limited frequencies. So pulse shaping means what it will do is it will change the shape of this pulse. Instead of rectangular pulses, it will take some smoother pulses like this. Okay, how exactly pulses we have to take, I'll show you that later. So rectangular pulse. Okay, don't think of this as sinusoidal signal. I'm just giving you for example's sake. Okay, something like this. Don't. This is not a sinusoidal signal. I'm going to take some pulse. Okay, what should be the exact shape of the pulse, that we will discuss later on. Okay. Now, so this negative rectangle, instead of negative rectangle, you're going to take some pulse shape, some which is negative in amplitude. So next again, positive pulse, negative pulse. Instead of positive rectangles, you are going to send some positive pulses. Instead of negative rectangles, you're going to send some negative pulses. What is the advantage of this pulse shaping? What is the advantage is the signal becomes band limited. Here, the signal is not band limited. So the advantage of pulse shaping is what pulse shaping does is it will convert rectangular pulses into smoother pulses, or it will convert not band limited signals to, or signals which are not band limited to, band limited signals. Because of this, if you pass this through a channel, since this is already band limited, if you pass this through a band limited channel, what happens is ISI will not be introduced. Inter-symbol interference will not be present. Fine. So there are three pulse shaping techniques. One is sync pulse shaping technique. First one is sync pulse shaping technique. Second one is raised cosine pulse shaping technique. And third one is Gaussian pulse shaping technique. There are three pulse shaping techniques that we have. And these two we are going to discuss in detail because they are really, really important. So problems can be asked based on them. And this is also important actually. We use this in practical in GSM. In global system for mobile, practically in all techniques, most of the digital communication techniques, we use pulse shaping. Okay, because this will help us to limit the bandwidth of the signal, which will help in avoiding ISI. Right. So we're going to use practically one of the pulse shaping techniques. So in GSM, global system for mobile, we are using Gaussian pulse shaping. The technique that we use in GSM is GMSK. G means Gaussian. Why they're saying Gaussian is because they're using Gaussian pulse shaping, and the modulation technique that they're using is MSK, minimum shift keying, which is a special case of frequency shift keying. Right. So we are not going to talk in detail about Gaussian pulse shaping because About Gaussian pulse shaping, you know what is the shape of a Gaussian pulse, right? It looks like a bell-shaped curve is what we call as a Gaussian curve. So the pulse shape of the pulse is going to look like Gaussian shape. So that's why they're calling it as Gaussian pulse shaping. So, but in our textbooks, they have not given any details about Gaussian pulse shaping. Means what are the parameters that we should consider, how to shape it. There is no formula as such, or there is no possibility of numericals on Gaussian pulse shaping. So that's why we cannot discuss anything more about Gaussian pulse shaping. Only thing that we can understand is the shape of the pulse that we are going to use in Gaussian pulse shaping will be having Gaussian shape. So numericals, they cannot ask you any numerical on Gaussian pulse shaping because nobody has mentioned any formulas or bandwidth formulas for Gaussian pulse shaping. So they have given formulas for sync pulse shaping and raised cosine pulse shaping. So we're going to discuss about these two in detail. And in previous question papers of GATE and ESE, lots of questions were asked based on these two pulse shapings. So let us start talking about sync pulse shaping. Okay, so look at this one. Instead of transmitting rectangular pulses, in time domain, how about transmitting sync pulses in time domain? So sync pulse shaping, what it is saying is convert your rectangular pulse into sync pulse. If you convert that into sync pulse in time domain it should be sync, not in frequency domain. Earlier it was rectangular in time, rectangular shape in time, and in frequency domain it is sync shape. Now, what we are doing is in sync pulse shaping, we are using sync pulse shape in time domain. So we are transmitting this pulse in time domain, whose Fourier transform will be rectangular shape. So I've written the exact Fourier transform here. So what is the null point here? TB. Reverse of null point will give the width of the rectangle. So reverse of the null point is 1 by TB. 1 by TB is nothing but RB. RB is the width of the rectangle. And what is the bandwidth of this one? It is just RB by 2. Whereas in the previous case, if you observe the previous case, the bandwidth in the previous case is different. Bandwidth is, if you're using rectangular pulse in time domain, in frequency domain it is sync, and the null point end is ending at RB. So practically speaking, we say the bandwidth of this pulse as RB. Okay. Whereas if you are using sync in time domain, so in for frequency domain it will become rectangle, then the bandwidth also has reduced. See the bandwidth? It is only half of the bandwidth that we are using when you are using rectangular pulse in time. So there are two advantages here. If you are using sync pulse shaping, the signal is becoming band limited, first advantage. Second advantage is the bandwidth also has reduced. There are two advantages. So minimum bandwidth happens if sync pulse shape is used. That's it. Minimum bandwidth happens. So in digital communication, many times they'll say minimum bandwidth. What is find the minimum bandwidth required to transmit a signal? So always remember this point. Whenever they say minimum bandwidth, you should understand that okay, they are using sync pulse shape in time domain. For every 1 bit, they are sending this positive version of this sync pulse, and for every 0 bit, they are sending negative version of this sync pulse. Okay, right. Instead of rectangular pulses, if you are sending sync pulses, bandwidth will be only half of what is required for rectangular pulse. Okay, when I say rectangular pulse, it is in time domain. In time domain, if it is rectangular, in frequency domain, it is sync. In time domain, if it is sync, in frequency domain, it is rectangle. Fine. So I hope you have understood the advantage of sync pulse. So now sync pulse means we write it as sync of something into t, right? So if you observe, sync of RB into t is the equation for this sync pulse. So you can observe sync of RB into t means it becomes 0 at multiples of 1 by RB or TB. You can observe. You can write this if you want further understanding how I have written this TB, 2TB and so on. You can understand that as sine pi RB into T divided by pi RB into T. You can equate this to 0. You can understand at what times it becomes 0. You'll understand that it becomes 0 at TB, 2TB and so on. And earlier I told you the relation between Fourier transform rectangle or Fourier transform of a sync. Whenever rectangular sync are there in time domain and frequency domain, the order can be reversed also. Width of the rectangle, inverse of it, will be decide the null point. Similarly, whatever is the null point of the sync function, you reverse it, that will give you the width of the rectangle. Okay, fine. So minimum bandwidth happens if sync pulse shape is used. In any problem, if they say minimum bandwidth required to transmit a signal, imagine that, okay, they are using sync pulse shapes. Okay, so how the transmitted signal looks like. Is this pulse shape okay? If you observe, I'm taking a width of the pulse. Width of the pulse is not TB now. Okay, everywhere there will be some disadvantage. Okay, earlier in time, the bandwidth in time, it is time limited. Okay, if you observe the signal, this signal is limited in time. That's why it is not limited in frequency. Okay, but now the signal is little different. The signal is little different. Here in time domain, the signal is not limited. In time domain, the signal is unlimited, which is making the signal limited in frequency domain. The signal here is unlimited in time, which is making the signal limited in frequency. The same signal only, but in time domain, if it is unlimited, in frequency domain it becomes limited. Okay, fine. So if you observe, anyway, it is, if you want to make the signal limited in frequency domain, it should have to be unlimited in time domain. Fine. If you observe this, the width of this main lobe itself is 2 TB. But how much time are we allowed to use? Only TB, right? Because TB is the bit time. But here we are using a pulse which is having more width than TB. But still, that is also fine. So how it is fine, we'll see. You'll understand when I take more pulses and plot it. So let me say I'm transmitting 101 bits. 101 bits. Okay, if I'm transmitting 101 bits, so what will we do at the receiver? At the receiver, we are going to sample at multiples of TB. We are going to sample at 0. We are going to sample at TB. We are going to sample at 2 TB, 3 TB, 4 TB, and so on. Here I have taken 3 bits only. 3 bits means we are going to send a positive sync pulse for 1 bit, negative sync pulse for 0 bit, and positive sync pulse for again 1 bit. But if you observe here, it looks like there is clear intersymbol interference. One symbol is definitely interfering with the next symbol because the width of the pulse is very large. Because the width of the pulse is very large in time domain, one symbol, first symbol is interfering with second symbol, third symbol, fourth symbol, fifth symbol, it is interfering with 10, 15 symbols. Similarly, second symbol is also interfering with 15 symbols that side and 15 symbols this side. Yes, it is interfering. But the design of the sync pulse is in such a beautiful manner that it is looking like it is interfering, but it is not interfering at the required places. What do I mean by this? See this one, this first symbol is interfering with the second symbol. Second symbol is definitely interfering with the first symbol, but it is not interfering at the point where we are going to sample. See, finally, at the receiver, what is our final idea? Our final idea is at the transmitter we want to transmit 101. So since we cannot transmit rectangles because rectangles will create ISI, what we are doing is instead of rectangles we are transmitting sync pulses. Sync pulses. So if you are transmitting sync pulses, it looks like there is ISI. But at the receiver, finally our agenda is to understand these bits only. These bits we are sending in this manner. At the receiver, by seeing this signal, we want to understand the bits. Can we understand them or not? For us to understand, we have to design these pulses properly. The sync pulse shaping is one such technique, very good, very well designed technique. So if you observe, at 0 if I am sampling, yes, I am getting at 0, the effect of only the first pulse is there. Second pulse interference is there, but exactly at the point that I am interested in, there is no effect. Second pulse is interfering with the first pulse, but it is not interfering exactly at the location that I am sampling. Similarly, second point, if you observe, at TB I am sampling at TB. At TB, we are having the effect of only the second pulse. The effect of first pulse is 0, effect of second pulse is also 0, and effect of third pulse is also 0, effect of fourth pulse is also 0. All the pulses are becoming 0 at TB. So here at TB, we are going to get the effect of only the second pulse, second sync pulse. So that's why it looks like there is ISI, intersymbol interference. Before transmitting through channel itself, it looks like intersymbol interference is there, but it is not exactly there. At the points where we are interested to sample the signal and decide the bits, at those points, intersymbol interference is not there. See this one? Here we are going to get only this sample, -5 let's say, and this is 5. 5 plus 0 plus 0, yes, it will be 5 only. -5 plus 0 plus 0, it will be -5 only. Now this one, if you transmit through channel, there is no problem because if you pass this band limited signal through band limited channel, there is no problem of ISI. Okay, so here similarly, here also it is 5, and here the effect is 0 only, right? So there is no intersymbol interference if you are transmitting sync pulses instead of rectangular pulses in time domain. And one more advantage is there is no ISI introduced by the channel, first advantage. Second advantage is bandwidth is limited bandwidth, very small bandwidth compared to rectangular pulses. If you're transmitting rectangular pulses in time, the bandwidth is RB. Whereas if you're transmitting sync pulses, bandwidth is only half of it. So always in any question, whenever they say maximum bandwidth, imagine that rectangular pulses are transmitted in time domain. Rectangular pulses are transmitted in time domain. In time domain, rectangular pulses are transmitted, so bandwidth will become RB. And similarly, if then whenever they say minimum bandwidth, understand that they are transmitting sync pulses. They don't need to explicitly say that they are transmitting sync pulses, but we should understand that. Okay. Fine. Okay. Now, let me talk about the problem with sync pulse shaping. What is the problem with sync pulse shaping? So we have talked about the advantages of sync pulse shaping. Sync pulse shape in time domain is limited in bandwidth. So that's why when you pass through band limited channel, there is no ISI. Very good. Sync pulse shape in time. In time, I'm talking about sync pulse is band limited. And hence intersymbol interference is not introduced by band limited channels. Very good. So you should understand that wireless channels are also band limited, because in wireless we don't have infinite bandwidth. Okay, we have to frequency division multiplex different signals. So every signal is allowed to occupy only certain bandwidth only, which means the wireless channels are also definitely band limited channels, not only wired. Here I've taken example of wired channel, but wireless channels also are band limited channels. So for wireless channels also we will be having similar problem. If you send rectangular pulses, since wireless channels are also band limited, you'll be having ISI problem. So that's why for wireless channels also, our signals, the signals that we are transmitting should be band limited in nature. Otherwise, wireless channels also will introduce ISI. Right. Now let us talk about the problem with sync pulse. So advantages, it is band limited, so hence ISI is not introduced. And one more advantage is bandwidth is minimum, and it is least possible bandwidth. You cannot reduce the bandwidth of the pulse less than RB by 2. If you reduce the bandwidth less than RB by 2, the width of the rectangle will reduce, which means the width of the sync function will increase. If it increases, what happens is it will not be ISI free pulse. Okay, it will not be an ISI free pulse. The pulse will not be a well designed pulse. So it will create new problems. So okay, the minimum bandwidth possible for any pulse, okay, for any pulse is only RB by 2. If the bit rate is RB, the minimum bandwidth possible is only RB by 2. Bandwidth is minimum, and minimum bandwidth is equal to RB by 2. But there is a problem also with this. Let us talk about the problem. What is the problem? The problem is, right. So I hope you know the concept of synchronization, timing synchronization. Timing synchronization is nothing but getting the timing. At what time you should sample, or what is the starting time of a bit, what is the ending time of a bit. Understanding that is what we call as synchronization. Once we start receiving, we will not be able to understand what is the starting timing and what is the ending timing of a particular bit. Okay, it's not so straightforward, because the circuit should understand it, right? A person is not looking at it and trying to understand it. Okay, even if a person is looking at it and understanding it, that is also going to be difficult. The circuit has to understand what is the starting point of a bit and ending point of a bit. Only then it can start sampling. So why should we understand the timing here? Because if you don't understand the timing, so how will you know? So here since I've drawn a line here, that's why you're able to understand that, okay, this is 0 time, this is TB time, like that, because I've clearly plotted. But when you receive the signal, nobody will write what is the timing, right? So you have to understand at the receiver what is the 0 time, what is the TB time, what is the starting time of a bit and ending time of a bit. Because only then you can start sampling, right? Only then you'll start sampling at the certain places, right? So for example, so by using some circuit, you'll understand the timing as 0 time, TV time, 2 TV time, something like that. Okay, you'll understand by using some circuit. That was using with the help of some circuit, synchronization circuit. You'll understand the timing of the bit, which means starting time of a bit, ending time of a bit, starting time of a bit, and ending time of a bit. Once you get the timing with the help of that circuit, what happens is you'll start sampling the signal. Okay, it's 0 seconds, TB seconds, 2 TB seconds. But there is a chance of an error, right? There may be chance of an error, right? Correct? Huh? If there is an error of timing, for example, instead of this as the starting time, if it recognizes this as the starting time, for example, if it recognizes this as the starting time, and then what happens? The gap is TB, so it will recognize this as the TB time, and it will recognize this as the 2 TB time. Instead of this as the 0 time, it will recognize this as the 0 time, which means there is some error in the timing synchronization. It is possible. Any circuit can make small errors, right? So if there is some small error in timing, if there is a timing error, even if you are using sync pulse, in that case also, if there is a timing error in synchronization, the meaning of it is, if you have understood the timing of the bits or starting or ending timing of the bits little wrong, then what happens? Try to understand this. So if you are understanding this as the starting time of this bit, then you are going to sample here. Then here also you are going to sample here. Here you are going to sample it here. Observe it carefully. So, for example, here you are supposed to receive 5. Because of timing synchronization error, you are receiving it as 4. And if you are sampling here, there is no problem because ISI from the neighboring pulses is 0 here. So if you are supposed to receive 5, you will receive it as 5 only. Along with noise, you may receive this way or that way about 5. But here, because of timing error, you are receiving from the original pulse, you are receiving only 4. And since there is a timing error, we are having ISI from the neighboring pulses also. See this one? Because of this pulse, you may get an error of some -1, let's say. And because of this pulse, you may get an error of around -2. So observe this one. What exact value are you going to receive here? If there is some small timing error, okay, then what happens? If there is some error in timing, instead of 5, you are receiving 4 from this first pulse. And because of this second and third pulses or other pulses, since I have done only 3 pulses, you are able to see this. But if there are many other pulses also, we will be having interference here because of remaining pulses also. So at this value, at this point, addition of all these signals will result in a value 4 plus -1 plus -2, which is just +1. Along with noise, you may receive that +1 as a negative value also sometimes because of noise. Right? So you are supposed to receive a positive voltage, but you may receive, with more probability, you may receive a negative voltage because of noise. So this here, ISE is being introduced, okay, because of timing synchronization. If there is timing error in synchronization, then ISI is present, okay. Whereas if there is no error, then there is no ISI, because at the samples, if you are sampling at the right places, there is no ISI. But if you are sampling at the wrong places, then definitely there will be ISI, because the sync pulses are in such a manner that they are interfering with each other, but they are not interfering at 0 time, TB time, 2 TB time, and so on. Exactly at particular time instants only, they are not interfering, but they are interfering in the remaining places. If there is error in synchronization, which means you are understanding the timing wrongly, which means you are sampling at wrong places. If you are sampling at wrong places, definitely you'll be having significant amount of ISI. Because of this ISI, what is the problem? Because of this ISI, what happens? Errors will increase. Earlier, if you are getting only 1 error, now you will be getting 2, 3 errors. Probability of error will increase due to ISI. Probability of error will increase. I'm not saying all bits will be in errors, but number of bits in errors will increase. Earlier, out of 1000 bits, if 1 bit is in error, now if out of 1000 bits, there will be 4 or 5 errors. The probability of error will increase. Right? How to overcome this problem? So using just sync pulse shaping, we cannot reduce the ISI because of timing error. Because of timing error, sync pulse cannot help us. If there is no timing error, sync pulse is the best pulse. Okay, right. Sync pulse is the best pulse in terms of bandwidth. Okay, sync pulse is band limited. Sync pulse is band limited. That is an advantage. So if you pass through band limited channel also, no ISI is introduced by the channel. Second important advantage of sync pulse is that it is having the least bandwidth possible. Right. But the disadvantage is if there is an error in timing synchronization, then we are going to have a problem. We are going to have huge amount of ISI. So how to avoid this ISI due to sync pulse? That is the main point that we have to understand. So for this sync pulse, if there is timing error, we are having ISI, we should figure out a way how to reduce this one. Yes, we can do that using our next concept or next pulse shaping, which is raised cosine pulse shaping. It is a little advancement of sync pulse shaping. We call it as raised cosine pulse shaping. Mostly the problems will be based on raised cosine pulse shaping. So this is an advancement of sync pulse shaping. What we do here is, even if there is timing synchronization error, still we are going to reduce the ISI. We cannot eliminate this ISI because of timing synchronization error, but what we can do is we can only reduce it as much as possible. Okay, how are we going to reduce it? Let us try to understand. I'll give you some idea, and we will discuss it in the next session. So there will be a continuation session for this. So after half an hour, I'll be starting the next session. So I'll talk about raised cosine pulse shaping and the ISI free condition. How to design a pulse which is ISI free. So that also I'm going to talk about. Questions were asked based on this condition also, ISI free condition also. And I'll talk about that. Right. So I'll give you a rough idea of how to design this raised cosine pulse. So if you observe, there are errors. If there is a timing error, then definitely you're going to get ISI from the side loops. So mostly the side loops. From the fourth pulse also, side lobe will introduce the ISI here. So that's why what we can do is somehow by doing something, if you can reduce the width of the side lobes, and if you can narrow this pulse, if you observe this pulse, if you can narrow this pulse, this main lobe, if you can make it narrower, then definitely what happens is this ISI will reduce. So what I'm trying to say is, by somehow, if you can reduce the side lobe amplitude, then ISI because of this pulse will reduce. And if you can make this pulse narrower, if not, it's not like this, but if you can make it narrower like this, if you can make it a narrower like this, what happens? Earlier, this was the sample from this pulse. Now it will be a smaller sample, right? This pulse also. If you can make it a narrower pulse like this, then the ISI will be reduced a lot. The rough idea of raised cosine pulse shaping is we are going to change the sync pulse only a little bit in such a manner that the main lobe will become narrower and the side lobes will become, the amplitude of side lobes will reduce significantly, so that the ISI which is introduced because of timing error can be reduced significantly. We cannot completely eliminate it, we can only reduce it significantly. Okay, right. So we have understood till now about the problem due to band limited channels when you transmit rectangular pulses, and how to avoid that problem also we have understood by using the concept of pulse shaping. So we have discussed about one pulse shaping, which is sync pulse shaping. So in the next session, which will start in another half an hour, we'll talk about the next type of pulse shaping, which is raised cosine pulse shaping. So before ending the class, okay, here in every slide you are seeing this code. This code you can use if you want Unacademy Plus subscription. You can use this code for 10% discount, and you can follow me on this page, Dinesh space Gutha. You can type Dinesh Gutha in Facebook or in Telegram channels. You can find me on Facebook and Telegram. So if you have any questions on communications or signals and systems, you can ask me in these groups. And if you want to subscribe for Unacademy Plus, you can use this code for 10% discount. Right. So these are the courses that I'm taking on Unacademy Plus: analog communication, digital communication, random variables and random process, and noise analysis and communication. Right now I'm taking random variables course on Unacademy Plus platform. I'm taking live classes every day 9 p.m. to 11 p.m. So why should we take subscription? Okay, so if you're not sure how will be the classes, you can subscribe for only 1 month. You can see how is the quality, and then you can subscribe for more months. So this is a huge advantage. If you see the fees, so faculties like me, we used to teach from ADC, Academy, and all the big institutes. So the places that we used to teach, there they used to charge 80,000, 90,000 for coaching of GATE and ESC. But whereas here the fees is only 1/4 of what major institutes are charging. Only 1/4. If you observe, 6 months you can complete the course. The fees is hardly 20,000. And if you are not confident in 6 months, you can take another 6 months or 1 year subscription, which will charge only 25,000. Whereas in Medici, if you go, or Ace Academy, if you go, only for 6 months course, they're charging around 80,000. And there you have to travel, you have to spend extra money. But here there is no such disadvantage. Here you can sit at home, you can listen to the classes multiple times. Here there will be live classes, there will be recorded classes, and there will be multiple teachers for the same subject also. If you don't like one teacher, you can listen to others teacher also. Right, there are huge advantages. So I can with 100% surety I can tell you it's worth every penny. So if you don't have a subscription, you can take the subscription. And anybody whoever feels like studying and preparing for any competitive exam seriously, you can take an Academy Plus subscription. Not only for GATE exam, for other exams also, an Academy is running a beautiful courses. So if at all if you want subscription, or if your friends want subscription, you can refer them my code for discount. Okay, you can follow me on Unacademy Plus platform. You can type for my name, so you can follow me so that you can get updates on my free classes as well as Unacademy Plus classes as well. Okay, thank you guys. I'm going to stop the class at this place. So we'll continue the class after half an hour. There will be a follow-up session. Thank you so much. Have a nice day.